the old days, automotive power supply meant figuring out how big a wire you needed to hook up to the 12-volt battery. Let's see, how about this little 14 gauge? Whoa, dang, blue smoke. Okay, let's try a bigger one. That smells bad. Oh. Most of the stuff we were hooking up was pretty happy with anything between about 10 volts and 16 volts. Those 8-track players were pretty solid. You could rock out to your Grand Funk Railroad even when the alternator was dead and your headlights had dimmed to a pale yellow. Play that funky music. Okay, never mind. Hi, I'm Amelia Dalton, host of Chalk Talk. These days, we're putting all kinds of sophisticated electronic systems into cars, and it seems like everything we design has a slightly different power requirement. And we need some help getting precise, efficient, reliable, low-cost power regulation. My guest today is Vik Patel from Infineon, and we're going to dive into the diverse world of automotive power supply. So grab yourself some booster cables and let's get started. And before we get started, don't forget to click that link. There you can find out more information about automotive power supplies from Infineon. Hi Vik, thank you so much for joining me today.
Hi, thank you for inviting me.
Okay, so I understand there are basically two classes of voltage regulators depending on our application. Can you start off explaining that?
Sure, there are two major categories that we cover here. One is the linear voltage regulators, which you see on the left there, and then on the right you see DC to DC. Starting on the left with the linear voltage regulators, there are actually 4 subcategories that we can offer. One is the battery connected application, i.e. the maximum voltage input is 45 volts. Then there are what we call post regulators, i.e. they have something in front of them, another power supply, and they have a maximum VIN of 20 volts. Then we have a category called sensor supplies or trackers, which are basically voltage regulators without an internal band gap or reference, and I'll explain what they do in a little bit. And then there is a smaller category of application-specific devices. On the right side, you see DC to DC, and there are 2 major categories there. One is the standalone or single-channel buck converters or boost converters or controllers. And then on the right, what we call system supplies, which basically means multi-rail, multiple voltage regulators in one package.
It seems like the automotive industry, particularly the electronics part, is going through a dramatic change these days. I assume that pushes back into people like you who are supplying components. What kind of trends are you seeing in regulators for automotive use?
So on the very high level, it's all about energy efficiency. From government mandates for people who want the environment to be better, obviously we need to improve our efficiency. Now, what does that mean on a power supply level for a semiconductor guy and for a designer designing an automotive vehicle? Number one, it's really about the current consumption. We need to have less current consumption, especially in the sleep state. So this would mean a lower quiescent current. Number 2, we need lower power dissipation. So we need to really work on minimizing that dropout voltage between the input voltage and the output voltage of the device. Then, of course, everybody's looking to build things cheaper, right? Every year you get that nice phone. For some reason, you always pay the same price or even more. But most vehicle guys say we need it cheaper year in, year out. So a reduced bill of materials to implement this solution is what's required. So what does that mean on the power supply level? It's basically the output devices, how to make them smaller and more cost effective, how to deliver the same performance in a smaller package size. And then finally, something very specific in terms of requirements is what happens in cranking. So cranking, for those who are unfamiliar in automotive, is basically when you're turning the key and trying to get the engine started, the battery voltage dips down to a very low level. And this might go lower than the actual minimum input voltage that the device can start and work. So what we need to do is improve the range of our voltage that our device can operate within. Also, we need to improve our robustness because there are new requirements saying, hey, this device could see higher and higher voltages. We need it to survive this kind of condition and still operate. These are the 3 major trends we see, and the solution that we feel is the new voltage regulator families that you'll see in the next few slides.
Okay, I think I've got the high level idea down. Let's dive into some data sheets. Can you tell me about the specific product lines Infineon has in this area?
Right. So in terms of our power supplies, I will start with, of course, the linear voltage regulator group. And they have two new solutions or two new families which hope to answer some of the technical trends I discussed previously. So the first key features we needed to address were the ultra-low drop voltage. So this in our TLS 820 and 850 families is answered. A typical best-in-class parameter that we have is 70 millivolts at 100 milliamps. So hopefully this helps in terms of minimizing power dissipation and helps in terms of stop-start applications and cold crank applications. Then ultra-low quiescent current. So if you see on the slide, the 805 and 810 family, this is really tailored towards the ultra-low quiescent performance. You see a number there of 5 microamps, which is hopefully one of the lowest in the industry. And this helps you in energy efficiency. So for applications where you need to turn most of the module off, but you need to keep alive a little bit of current, this is the guy that you use, the TLS 805, and it keeps that quiescent current down, and it helps the car maker extend his battery life. And of course, the last thing is robustness. You really need excellent line transient robustness in an automotive application. It is a noisy environment. You're going to get a lot of voltage spikes. So these new families have a lot of increased protection and robustness on the input side, so you don't need to put so much capacitance in front of it, i.e., less bill of materials.
Tell me about the 820, 850 ones. What are some of the key advantages there?
Some of the key application advantages of the 820 and 850 family are, number one, the fact that you only need a 1 microfarad ceramic to keep the regulator stable. Now, in the past, we could see that you needed an electrolytic 22 microfarad to keep our devices stable. So we've moved to a different technology that enables this smaller and lower cost capacitor on the output. But hold on, you say. Everybody says that. Everybody says their regulator works with a 1 microfarad capacitor. So as you can see on the two graphs here, I've taken the TLS 820 in this case, turning on basically a load, a 5-volt load, and on the right, a competitor's performance. And what you see really in terms of a competitive advantage is, yes, both of them use a 1 microfarad capacitor, but ours actually turns on in time. If you look at the competitor performance there, it takes a little too long maybe to turn on. In this case, it was a microprocessor. So yes, we do work with 1 microfarad capacitors, and we have a faster reaction time on load change.
All right, so if I want a 5-volt output, what are my specific options?
So here we come to a selection table that we have generated internally. It's basically going by output current class on the top, starting at 50 milliamps all the way up to 500 milliamps. And then we have it selectable by feature size. So going from a no feature version to just an enable version, enable and reset, or the full feature device, which is enable, reset, and an integrated watchdog. And here you have the devices that are available, starting with the TLS 805 on the left side, all the way up to, in the right bottom corner, the TLS 850F0TA. Bit of a mouthful, but that is really the high-end device which can provide 500 milliamps and have an integrated watchdog and enable and reset. Now, you ask, well, how do I get hold of this? So number one, you should contact your Infineon rep. Failing that, number two, there is an online version that you can access, and I will get to that at the end of this presentation.
Now let's jump into post regulators. What are post regulators, and Vik, why would I want to use one?
Right, so post regulators, believe it or not, don't come in the mail. They actually are, in terms of a system architecture, described as a regulator with a minimized input voltage range. They're used behind a pre-regulator, so hence the pre and post nomenclature. So why do you need pre and post architectures is the question. So as we develop into more and more advanced cars with more and more features, the number of electronics go up, but also the level of the electronics goes up. So hence the amount of power that's required goes up. We cannot deliver this kind of power just in a single regulator connecting battery to whatever it's driving these days. So you have to split it up into a pre and post architecture, as you see there on the slide. And this enables basically the heat to be distributed across the module. This is why you now see in things like infotainment, where you have the nice little displays in the front, and the driver assistance systems, a pre and post architecture. So just going into why use Infineon's versions, people out there in the market have CMOS regulators, which go up to 7 volts on the input side. Ours goes up all the way to 20 volts, which could be an advantage, especially in a short circuit condition. If you have a short on your pre-regulator and battery is now connected to your post regulator, a 7 volt device may fail quicker than a 20 volt device. This may give your system enough time to react to the short and shut things down. The other key ingredient, all of these devices we're talking about are automotive qualified. You have automotive reliability and, of course, automotive support, which are key differentiators. And, of course, then certain variants, as you will see later, are in a leadless package with automated optical inspection. So you don't need an X-ray machine to understand if the device is soldered to your board or not. So this is, again, a competitive advantage.
Okay, can you take me through some specific options with these as well?
Sure. So similar to the battery-connected regulators, we have another table here by output current and by feature set. So here you start with a very small TLS202, 150 milliamp output, no feature at all, and it's in an SCT595 package, which is a 2x2 package there. You could see the package overview in the bottom corner there.
Now, you also mentioned voltage trackers. What's the deal with those?
So voltage trackers, I mentioned voltage trackers. Now some people call these sensor supplies, similar thing. We just call them trackers because essentially this device tracks the output voltage of another voltage regulator. So why use voltage trackers, or why do you need sensor supplies? Basically, if you have power supplies, as you see in the diagram there, providing power to external sensors, there's wiring involved in between this ECU and the sensor. And if there is a short circuit on that wire, this will basically pull down the power regulator on board the ECU. Now, if you have only one main regulator, which powers your microprocessor and also these sensors, and you get that short, guess what? Your micro is down, your whole ECU goes down. So most people basically use a sensor supply or a tracker, which is not connected to the main VREG. And this is protected for short circuit and also protected for reverse polarity. And it's basically an independent path. So in case you do get a short on your sensor, then you do not take down the main power supply and your module is still operational.
All right, I think I've got the big picture on trackers. Can you give me a detailed rundown on the options with these as well?
Looking at the product family that we have, there are at least 5 from the old class, so what I call the TLE 4200 family, starting with one of the most popular ones out there, the TLS 4250-2, 50 milliamp tracker with a tracking accuracy of plus or minus 0.5%, and a minimum adjust voltage of 2.5 volts, again in this SCT 595 package. And you see as you go through from 50 to 70 all the way up to 400 milliamps, you have a family of trackers in these various packages from the small one to the large D-squared pack. What we have coming out is a new tracker, 150 milliamp device. And now let me go to that in more detail. So this one actually has a VN range of minus 16 to 45 volts, i.e. it's reverse battery protected, and it also has some current limit and current protection. It has a temperature range like all of these, full automotive temperature range, minus 40 to 150 degrees C, and a higher tracking accuracy of 0.1%. Now, what did we do different in this device versus the old TLE 4200 family? Number one, replaced the single pin we had for adjustment and enable and separated them out. So now your enable pin can be as simply connected to an I/O, a general purpose I/O on the microcontroller, which is an easier system design. The other thing we added was a voltage monitor. So what we're seeing with these post regulators is more and more requirement basically to be in a functionally safe system, i.e. to know what is going on with the output voltage and to be able to monitor that. So that's a key requirement coming up, and we've added that into this sensor so you can now monitor what is being supplied to the sensor.
Now, what if my application is really tight on physical space?
So here's a page basically giving the package overview of these post regulators. And as we can see, we have a wide selection possible. You have the larger packages for the higher power devices, but as you mentioned, board space is a must. So really look at these two packages. I've mentioned the ST595, which is a 2x2 package, but we also have a new leadless package, which is a 3x3, very small footprint, so essentially 60% smaller than the equivalent standard leaded package, the DSO8, and it has a decent power capability, 53 Kelvin per watt in terms of the thermal resistance. And of course, the thing we do with all our leadless packages is we offer automatic optical inspection. We have an extra process step where we carve out some additional stuff, and this gives you the ability to have this device go through AOI, i.e. a camera on the line, which is a lot cheaper than having a huge X-ray machine.
Okay, a lot of automotive systems today involve RF, and that means antennas and stuff, and that opens up a whole can of worms with power supply design, right?
Right, so here we come to the category that I mentioned in the beginning, which was application specifics. Now, this is one example. There are more, but today I'll cover the RF antenna, active antenna supplies. So what we're seeing is as automotive moved in the 90s from the fixed aerials that you used to see to these nice little shark fin antenna that you see on the modern cars, the challenge to the designer for those shark fin antennas is in terms of the wiring, the load and the supply are not in the same place. So you have to really monitor what's going on. So you cannot just give a power supply. You have to have a power supply with the capability to monitor the load. This is where our solution is the TLE4277 family, which is an active antenna driver. This also has accurate current monitoring integrated on board, and we claim it's around 5% in certain current ranges. And we're working to improve that across the entire current range. But essentially, this can monitor your remote antenna wherever that may be because it has the current mirror capability and it has the simple diagnostics, i.e. a real-time error flag. It can tell the micro, hey, this antenna, I don't detect it working, or there's some problem in the system. Please do something about it.
Can you give me an overview of this family?
Yeah, so essentially we started off with the original device, which was the TLF4277E. So this was a 200 milliamp device with a 20% accuracy, and it was designed into FM and digital tuners. We decided we had to improve that accuracy, so the second generation device, which is just being released, is the TLF4277-2EL, again in the same 14-pin exposed pad package. Here the accuracy became 10%. And of course, we're working on a leadless version because you mentioned space is always a critical thing these days, and they're trying to make smaller and smaller modules. So we're putting the same silicon into the TSON10 3x3 package. Now, what's not on the slide is actually what's in concept. So where are we going next? We're going to have dual versions, so two of these devices in a single package. And then we're looking at alternative multi-channel variations of this. But the idea is we offer for systems that need one, we have single channel available. And for systems that maybe have three, we have a dual and a single available. So you can complete the design with Infineon.
Earlier, we talked about linear as well as DC to DC. Let's dive into the DC-DC side now.
Sure. So essentially, we have two different subsegments of DC to DC, which are the standalone, as we call it. So this is a single channel, either buck or boost converter or controller. So we have a wide VIN up to 60 volts on some devices. A lot of the devices are 45 volt. The highest output current it goes up to is 10 amps on the controller side. On the converter side, you're in the range of half an amp to 2 amps. You have, again, certain features like reset and a watchdog timer integrated. And of course, the focus, especially for body applications, is this lower and lower quiescent current. On the system supply side, so what is a system supply? Basically, it's this pre and post regulator put together in one package. And you have multiple rails, so you basically have 5 to 6 voltage regulators in a single IC. Really designed to drive or deliver the power for the system. So your microcontroller, your communication IC, your sensors, all get their power from this system supply. And then you see on the bottom bullet there, this ISO 26262 product qualification. I'll get into that in a little bit. But essentially, functional safety has reared its head in automotive, and we have to meet this requirement for certain safety critical systems. One question I think people will have on their mind is, well, what's the differentiator? So automotive grade, I have to stress that we are automotive grade with all of these power supplies up to 150 degrees C. We have an optimized feature set for automotive, and of course we also support locally in terms of application support for automotive. Of course, Infineon is known for robust implementation and good quality, so we have one of the lowest DPM or failure rates on the market. And really, we are focused on automotive, and we have been for the last 25 years. So now I jump into a couple of examples. This is the 10 amp device that I just previously mentioned. It is a synchronous buck controller. An output of 10 amps is capable. Actually, it's a range from 2 to 10 amps, depending on the size of the FETs that you use externally. You have an adjustable switching frequency from 100 kilohertz to 700 kilohertz. And you also have a sync input if you want to synchronize to something external. You have the ability to shut it down with an enable, and you have very low quiescent current in this state, less than 2 microamps. And of course, you have an integrated soft start function to try and avoid overshoots. As we mentioned, we have an AEC qualification of grade 1, which is minus 40 to plus 150 degrees C. In terms of benefits, so we have a current limit topology that is flexible. You have a choice of either using the normal traditional route, which is the shunt resistor, which can give you a nice high level of precision, or if you don't want to use a shunt resistor, you can just use the high side path of the MOSFET, so you do not require that shunt resistor. And we are targeting, in terms of applications, a general purpose pre-regulator for all applications, but where we see it used most is in infotainment, in the cluster and the dashboard, and things like USB supplies. Next example, so this is an entire family of high frequency switchers. Now, what do we mean by high frequency? You saw the last device goes up to 700 kilohertz. Now people want to design above 2 megahertz. So they want to avoid the AM band and any interference that could cause from these switchers to that band. So this device has a range of 1 megahertz to 2.5 megahertz. And it's a class or family of devices that give you 500 milliamps at a fixed 5 volts. Now we're targeting body applications where quiescent current is a must, so here we achieve in general less than 45 microamps at the nominal battery voltage. We have an integrated MOSFET in this case, unlike the controller I showed you previously. It's an asynchronous topology, so you have the MOSFET internal and the catch diode external. In terms of the mode, it's current mode PWM regulation, and it does have the PFM mode for light load current. Input voltage range is 4.75 to 45 volts. So in general, 12 volt battery applications, this is a good fit. And in terms of the entire family, you have again the selection of either enable, reset, or watchdog functions, all in the same pin out. So you could start with one and transfer over to the other without having the need to rip up your PCB and do another layout.
Okay, now let's jump to a higher level for a bit. Let's talk about overall system supply. I've got my car battery here, and whoa, this thing is heavy. Now what?
Sure. So let me just explain visually the concept of a system supply. Where previously I showed you discrete post regulators, which would go behind a pre-regulator. Some people just want to have one IC that does both. So you can connect battery on one end and you can connect the outputs to your loads on the other end. So this is the example I show of a buck converter being the pre-regulator, and then you have some secondary linear regulators and some sensor supplies as your post-regulation, all put into one IC. So talking about a real world example of this, the TLF 35584 system supply for safety relevant applications, nicknamed the hypersonic. So this is an example of a system supply, but also the first example of a system supply done in accordance to the new ISO 26262 spec for functional safety. So when you are in safety critical systems, as you see in the bottom corner there, like power steering, braking, suspension, domain control, here you need some redundancy. You need the ability to basically put your system into a safe mode. Well, what does that mean in the real world? That means, for example, if your power steering fails, your primary path, which is basically your micro, you still need something on that board to be able to put the entire module into a safe state. So if you lose your micro, you have this device, which if you see here on the right side, it has an external safety path. So when it senses that the micro is not working properly or something's gone wrong, it enables a secondary safety path so that it can put your system into a safe mode even with the loss of a micro. So this is one of the requirements of ISO 26262, and this device has that functionality built in. Going back to the power supply section of this, it is a synchronous DC to DC with a very wide range of input voltage, 3 volts to 40 volts. It has a boost pre-regulator, which is in series basically with the buck, and if you need it, you can put in MOSFET and activate that boost. When it's not needed, it's just a pass-through, and then the buck activates, which is a synchronous buck, so you have the MOSFETs integrated, and they provide an output of 1.3 amps, and you can select the frequency range from 300 kilohertz all the way up to 2.5 megahertz. Then you have all these post regulators. You have the micro supply, you have a reference LDO, which is a plus or minus 1% accuracy. Generally, people connect this to the ADC of their micro. Then you have 2 sensor supplies, 5 volts, 150 milliamps each. And of course, you have the communication supply, 5 volts, 200 milliamps, which in general should be enough for 2 CAN ICs. You do have a small standby supply, 3.3 or 5 volt at 10 milliamps for keep alive. So of course you have all the safety features, which we can go into at a later date, but it's about a 200-page data sheet, and this guy is basically sold along with our Oryx microcontroller family as a companion IC. It is the latest example of system supplies from Infineon.
Now, more and more systems are being designed with 24 volts instead of 12 these days. What can you tell me about my 24 volt system power supply?
Sure, so let me start by differentiating the need that we see in the market. So in general, most vehicles that are sold to the consumer today are on 12 volt systems. Where we see 24 volt coming in or is used already is in commercial vehicle and agriculture. So here you have a higher voltage class, so the 24 volt systems are used. So we need a dedicated family of devices. So here I show what we have today in terms of 24 volt supply solutions, starting on the left with the LDOs, i.e. the linear voltage regulators. We have single channel TLE 4271-2 and 4267, and also a dual TLE 4471. These are robust. They're in our older bipolar technology, and they have overvoltage lockout to stop any voltages higher than those 58-60 volts required. And you have, again, a various feature set, either enable, reset, or watchdog available in those families. In the middle, you see a DC to DC that can operate up to 60 volts. So this has been designed into 24 volt systems. Again, with the robust design, you have the current limitation, and you have an advanced feature set. And this, I stress, is a controller that drives an external MOSFET. And again, on the right side, we have seen instances where you use the TLE 6389 as a pre-regulator, and then you can use our entire family of post-regulators, as I previously mentioned.
Okay, so if I'm thinking of using one of these solutions in my next design, where do I go for support?
Good question. Basically, here's the link, and you can find a solution finder, and in fact, the solution finder is for every product class in Infineon. But as soon as you go there, you will see a category voltage regulator. And you can click on that, and then you can put in the parameters that you require, and it will basically show you a search list of the best fits. So hopefully within 3 clicks, you'll be able to find the correct voltage regulator for your needs.
Great. Well, I think that's all I have time for today. Thank you so much for joining me, Vik.
Thank you.
And before we go, you didn't forget to click that link, did you? There you can find out more information about automotive power supply solutions from Infineon. For Chalk Talk, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the on-demand section of EE Journal or check out YouTube, keyword EE Journal.